Okay. What are Lewis diagrams used for? Well, we said shape determines function, and Lewis structures are limited to being able to allow us to predict the shape. And if we can predict the shape, then we can predict the pathways under which reactions occur and the type of products that we get. And so that topic of the pathways is really a second or third year college topic. But it's good to understand the principle that shape determines function, and Lewis structures allow us to predict polarity, and polarity is how the material is going to interact in its environment, especially a water environment. So, here's the concept. Suppose we had a Lewis structure, and let's say we had a central atom. I'm just going to call it X, and that we have it bonded to 3 other atoms, and then we have an unshared pair here. Well, each of these components consumes a certain amount of space around the atom. And in this particular model, there's 4 areas of space. And the theory is that since these are electron pairs, we know that electrons tend to want to, when they get close together, spin in opposite directions. But there's only 2 directions they can spin in, and therefore, if this unshared pair, for instance, has an electron spinning up and an electron spinning down, then this bond that's created right here also has an electron spinning up and one that's spinning down. So if they get near each other, the 2 electrons that are spinning in the up direction, what we call parallel spin, they interact and they create a tremendous amount of energy and a tremendous amount of repulsion. So the 4 things that are connected to the central atom are trying to spread out as far as possible. And when you spread 4 things out as far as you can, you don't spread them out into a square 90 degrees apart. You actually spread them out in 3-dimensionally into what's called a tetrahedron. So you would have the central atom, and then you would have the unshared pair and one of the atoms in the same plane. And that's what straight lines mean. Straight line means, ooh, I drew a curvy line. Straight line means in the same plane. And then this other atom would come out towards you, and this last atom would go away from you. So you would have one atom coming out towards you in the plane, one atom going away from you, and then 2 components that are in the same plane. So whenever they use a wedge, they're trying to say that the atom is coming towards you. And if they use dashes, it goes away from you. And this is called a dashed, or I'm sorry, not dash, a dash wedge diagram. And what a dash wedge diagram does is it shows 3-dimensional orientation. In other words, how they're spaced from each other. Now, Lewis structures don't show 3-dimensional orientation, but we can use them to predict 3-dimensional orientation. The best way to spread 4 things out around a central atom is into the 4 corners of a tetrahedron. So we would say that particular one falls into the tetrahedral family of shape. Now, if you had something like, in the last one we did boron trichloride. Drawing our little unshared electron pairs here. So you focus on the central atom. It's the central atom that determines the geometry of the molecule, and it also determines the polarity of the molecule. So in this case, we have 3 chlorines, so we have 3 areas of space that we have to accommodate. 1, 2, 3. And the best way to spread 3 things out, if you have a central atom, is to spread them out into the corners of a triangle. So this creates a bond angle between the chlorines of 120 degrees. And we call this the trigonal planar geometry. Whereas in the last one, if we spread things out into the four corners of a tetrahedron, instead of being 90 degrees apart, now they're 109 degrees. So that's better than 90, right? We spread things out. Electrons want to get away from each other, the electron pairs, so we spread them out as far as possible. And this concept of spreading things out is called Vesper theory. That most molecules, and I'm going to put a little star next to it because it's not all. Remember, there's 14 million different compounds, and they're not all going to follow these simple rules that we're teaching you in Chem 1 honors, but most of them do. Vesper theory, it stands for valence shell electron pair repulsion. I don't care if you know what the abbreviation stands for, but it means we're going to spread things out. And I always said to think of it sort of this analogy. You go into a movie theater, well, not now, but back in the day, go into a movie theater, and if the theater is empty, if you really want to upset people that are there, sit right next to them. People don't like that. They like to spread out from each other. And so if you go in there with your friend and somebody else is in there with their friend, you sit right next to them. That's going to make them very uncomfortable. Electrons are kind of the same way. They want to spread out as far as possible. And spreading them out reduces the amount of repulsion, and it reduces the amount of energy in the molecule. So now the molecule has two ways of reducing energy. We can form a chemical bond, so we can bring a negative closer to another atom's positive, and that'll release energy. And then spreading the electron pairs out as far as possible also reduces energy. Awkward. Okay, so here we go. So this theory, electron pair repulsion. So we go back to our little slideshow. Electron pairs spread out as far as possible, and that's going to reduce the amount of electron-electron interaction. That's going to reduce the energy in the molecule. And remember, Pauli said that when you get two electrons close together, they got to spin in opposite directions. So as soon as you introduce a third electron or a fourth electron, they're going to spin parallel to the two electrons that are already there. And that's going to create a tremendous amount of repulsion. So parallel spinning electrons, we want to spread them out as far as possible. And we have an issue with unshared pairs. Electron pair repulsion is not equal. Any two electrons or any three electrons. It depends upon the situation. For instance, when you try to get an unshared pair near another unshared pair in a central atom, and again, we're only focusing on the central atom, the terminal atoms do not dictate geometry. They do not dictate polarity. It's always the central atom that you have to look at. But if you have unshared pairs of electrons around the central atom, that's going to create a lot of repulsion. An unshared pair near a bond or a shared pair is a little less repulsion. Two bonds near each other is even less repulsion. And then if we have an atom by itself, two electrons spinning in the same orbital is the least amount of repulsion. All right, so we're going to start with looking at the geometry of materials that do not have an unshared pair. And there's really 6 families of geometry we're going to deal with. There's more than 6, but in basic chem, we're just going to deal with the 6 most common. The first one would be a linear molecule. Now, a linear molecule has a bond angle of 180 degrees, and there are 2 types of linear molecule. If you go terminal to terminal, so X bonded to X, then there's only one bond here. There is no central atom. This has to be 180 degrees in terms of the bond angle between them. Another type of molecule that will give you linear is, let's say we had something like beryllium difluoride. And I'll draw in my little electron pairs. Remember, beryllium is an octet violator, so it only needs 4 electrons to be stable. And so what we're looking at is we're only looking at accommodating 2 things. The bonds to the fluorines, we're going to spread them out as far as possible, so they're going to be on opposite sides of the beryllium, and that's going to create, again, a bond angle of 180 degrees, linear family. These are pretty rare. The most common geometries are going to be the tetrahedral, where you have four things around the central atom, because if you have four electron pairs, that's 8 electrons. That's the octet rule, which is the most stable. So tetrahedral family is going to be the most stable. All right, second type is called trigonal planar. And in a trigonal planar molecule, we're looking at, again, a central atom, and then that atom is connected to three other things. Doesn't have to be another atom, could be an unshared pair. But we now have to accommodate three areas of space. And so three things around the central atom are best spread out 120 degrees apart into the corners of a triangle. Now, trigonal planar is an important geometry because a lot of materials that are tetrahedral are already stable. In order to create, for instance, pharmaceuticals, what we have to do, we have to make them unstable. And by pulling off one of the four atoms on a tetrahedron, then we create a trigonal planar. And what that does is that allows particles to get in there and attack the central atom and create new molecules. The fourth family is the tetrahedral family. And in terms of a Lewis structure, we would have a central atom, and then we're going to bond it to four other atoms. And we said we're going to use three-dimensional space. Now, my wife is going tomorrow, Thursday, to, we're actually donating the Department of Education and Department of Health has asked all the high schools if they can donate some of their vinyl and latex gloves because of the pandemic, and then we're going to, of course, replace them later. So we're going to donate quite a few boxes of gloves, and so my wife, who's the department chairperson, is going there to collect them all. So I'm going to ask her to pick up a modeling kit so I can show you in three-dimensional space with another video what these things look like. So for now, you're going to have to kind of trust me and try to visualize it the best that you can. But tetrahedral, again, we said that we're going to spread four things out. And the way it works is two of the things are always in the same plane. And the third thing comes out towards you. And the fourth thing goes away from you. And then this creates a bond angle of 109, actually 109.5. But tetrahedral, I said, it's very stable because when you have four things, you have 8 total electrons around the central atom, which is the octet rule. So this is going to be the most common structure. And what else did I want to tell you about this? Nothing. Okay, fourth family. Now we go to our expanded octets, and we're only doing 2 of these families, the 2 most common. First one is something called Trigonal Bipyramidal. Now, once we start using the d orbitals, the easiest way to attack a central atom is by the north pole of the atom and the south pole of the atom. And we call these things that are connected north pole, south pole, we call them axial atoms. The rest of the atoms are what we call equatorial, which means around the equator of the central atom. So in trigonal bipyramidal, you're looking at 5 areas of space. And the first 2 are going to be on the north pole and the south pole. And then the other 3 we're going to put around the equator. And we're going to spread the 3 out as much as possible into the corners of a triangle. So for the last 3 atoms, or electron pairs, we're going to spread them out 120 degrees around the equator. So this creates 2 different bond angles. If we go from axial to equatorial, we get a 90-degree bond angle. So I'll show that in a different color. Let's go to orange. So axial to equatorial is 90 degrees, but around the equator is 120 degrees. So you have 2 different bond angles in the trigonal bipyramidal family. And then the last family, which is the most common expanded octet, is something called octahedral. And octahedral requires 6 areas of space. And again, take the same format. You have the central atom. We're going to put the first atom, north pole, second atom, south pole, axial positions. And then the 4 are going to go around the equator and spread out as much as possible, which means into the corners of a square. So this goes away into the corner of a square. This comes towards us into the corner of a square. This comes towards us. And this goes away from us. And so you wind up with only one bond angle. This axial to equatorial, we're going to call 90. You know what? I'm going to go back and change these A's into E's for equatorial. And then equatorial to equatorial, since they are in the same plane, squared out or spread out into the corners of a square, are also 90-degree bond angles. And octahedral is going to be the most common of the expanded octets. It shows up a lot of time in what we call organometallics, which are when metal cations interact with things like proteins. We get a lot of these octahedral substances. Now, I said that these are families. Okay, what do I mean by families? We said that unshared pairs, for instance, take up and create a lot of additional repulsion. So what happens is they distort the geometry of molecules. I'm going to use tetrahedral as an example. And in tetrahedral, if I was to do the Lewis structure for methane, we would put the carbon in the middle, and then our Lewis structure would have 4 hydrogens along the outside. And in terms of the tetrahedron, this would be a pure 109.5 degree bond angle between each atom. However, if we were to take one of the atoms and replace it with an unshared pair, like an ammonia, here's a Lewis structure for ammonia. Now we have an unshared pair on the nitrogen. Those other 3 bonds try to bend to get away from the unshared pair. So I think in your textbook, they kind of draw it like this, with a big loop around it, trying to show that the unshared pair takes up extra space. It doesn't actually take up extra space. You can think of it that way. It just causes extra repulsion and causes these other bonds to bend towards each other. And they say, well, okay, unshared pairs distort molecular geometry. Well, yeah, they do distort molecular geometry. And in fact, your book says, let's not even call this tetrahedral. Let's call this trigonal pyramidal. Okay, fine. Because in a tetrahedral, we're looking at a bond angle of 109.5 degrees. But in ammonia, you're looking at a bond angle of 107.8 degrees. That's not much different, 1.7 degrees. I mean, I'm going to make the video tomorrow that kind of shows you it's hard to take the model and only bend it 2 degrees out of 360. And yeah, it's a slight difference, and it does interact with a polar environment differently. But in terms of the type of reactions, if you're in the tetrahedral family, there are only certain type of reactions you can undergo, regardless of whether you're tetrahedral or trigonal pyramidal. So in AP chemistry, they've gotten away from saying, look, let's call ammonia trigonal pyramidal, let's call methane tetrahedral. As far as they're concerned, they're all in the tetrahedral family. So on my tests, you can either get this right by calling either one of these tetrahedral, or if you want, you can go with the trigonal pyramidal. Either answer would be correct. And then the last example in the tetrahedral family would be water. So we do H2O, and there are 2 unshared pairs. Now here's the thing. These unshared pairs are not 180 degrees apart. They're in the tetrahedral family. They're approximately, the bond angle here is about 106 degrees. I forget the decimal place, 105.8 maybe. But in any event, they're not 180 degrees apart like it looks like in a Lewis structure. Remember, a Lewis structure is not designed to show 3-dimensional arrangement. If I draw this using dash wedge, I put the oxygen in the middle, and I put an unshared pair and another unshared pair in the same plane, and then I would have a hydrogen coming out towards me and another hydrogen going away from me. And so what happens is these unshared pairs create extra repulsion and cause these two hydrogens to bend towards each other, and that's where you get your 106-degree bond angle. But again, it's only 3.5 degrees different from a pure tetrahedron as far as I'm concerned, and I've always taught it this way because that's how my college professors taught me. So when the AP board started teaching it this way, I felt kind of vindicated. As far as I'm concerned, they're all tetrahedral family, but your book calls a water molecule a bent molecule, and here's where they're getting the bent part from. They're saying if you start at the hydrogen and go to the oxygen and come back, you're just left with that little V, which is a bent shape. But as far as I'm concerned, they're all tetrahedral. Now, when you get to the expanded octets, the placement of the unshared pair starts to get interesting. For instance, in the Trigonal Bipyramidal family, and you don't have to know any of the other names. Bipyramidal family. You don't have to know any of the names of the distorted geometries, but if we were to have 5 areas of space, let's say we had 4 things bonded to a central atom, and then an unshared pair would take up the 5th space, where's the best place to put them? Axial or equatorial? All right, so you go back to our little diagram on Trigonal Bipyramidal. Well, let's look at the bond angles. It's 90 degrees axial to equatorial, but it's 120 degrees around the equator. So the equator would be, oopsie poopsie, the equator would be the best place to put an unshared pair. So I'm going to redo this diagram. I'm going to put my atom North Pole, South Pole, and then I'm going to put my other 2 atoms, again, this one going towards me, and this one going away from me. And then I'm going to put my unshared pair over here on the equator, because at least that allows the other 2 equatorial atoms to be 120 degrees away from it. And what you get here is something called a seesaw shape. So you kind of have to turn this sideways, and then this becomes the base of the seesaw, and then here's one person sitting on the seesaw, and here's another person sitting on the seesaw. I'm going to show you with the models, and it'll make a lot more sense, but you don't have to know that it's called seesaw. So suppose we added a second unshared pair. Where should it go? And again, the answer would be on the equator, because it's a 120-degree bond angle around the equator. Now for octahedral, it doesn't matter where you put the unshared pair, because they're all 90-degree bond angles. So we have our central atom. I'm going to put the unshared pair on the North Pole, and then I'm going to put the other atoms around the equator, the other 5 atoms. And what you get here is a square base with a pyramid at the top here where the other atom is, and they would call this particular geometry square pyramidal. But again, you don't have to know the term square pyramidal. You just have to know that when there's 6 things, regardless of whether one of the things is an unshared pair or the second thing is an unshared pair, that we're dealing with the octahedral family. Now your book has a chart in it that does a good job of summarizing all these shapes. So what do you have to do on the test? On the test, I would draw a Lewis diagram, and then you would say, well, all right, what's the geometry here? So if I drew something like the triiodide ion, so we go back to the example from the last video. So here's my iodine, and we have 1, 2, 3, and then we have the other iodine. And they say, okay, well, what's the geometry with respect to this? And the geometry, again, is always based on the central atom. So we look at how many things there are around the central atom. There's a bond, a second bond, and then 1, 2, 3 unshared pairs. That's 5 components. And whenever you're dealing with 5 components, the best way to spread them out is trigonal I spelled bipyramidal wrong. Hey. Bipyramidal. So you use the Lewis structure, you find the central atom, you count up how many components there are, and then you come up with geometry based on that. Sometimes they'll ask you for the bond angle, and in this case it would be 90 degrees axial and 120 degrees equatorial. I do want to go back and show you one thing about that, though, for the trigonal bipyramidal. What would the bond angle be if we went from axial to the other axial? Well, the bond angle would be 180 degrees, but they don't consider this bond angle because the distance between the atoms is so large that it becomes inconsequential in terms of chemical reactivity. That's not entirely true. It's only 99.9% true. There are things called chelating agents, but that is really advanced chemistry. Third year college. All right, so what did I want to say? Got the geometries, blah, 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 blah. Number of components. Okay, let's summarize what the components are in terms of area of space. Turns out any sort of single bond is equal to one area of space. And an unshared electron pair is also equal to one area. You're going to see a trend here. If you have a double bond, that's equal to one area of space. You're like, wait a minute, there's two bonds there. Yes, there's two bonds, but the way they overlap each other only consumes one area of space. It's a combination of what we call sigma and pi bonding. If you read the chapter, I'm going to go over that in my next video. And then a triple bond is equal to one area of space. Again, it's a way they overlap only consumes one area. So on the test, if it was FRQ, then you would draw the Lewis structure. I would ask you to predict the geometry, the bond angle, and then we'll talk about other things like sigma and pi bonds, hybridization, and that sort of thing in later videos. All right? Thank you very much.